Thank you to Andy and Dennis for inviting us over here. We are very, very excited. I'm Saraj Mudigonda, and I have my colleague here, Majid Bemanian. We're going to talk about MIPS Open and what it is all about. I'm going to provide overview of what it is, the licensing, and what are the different components. And I have Majid who will go into detail on the architecture side of things. So we are very, very excited, and the reason is obvious because it all started here. And I'm sure you all know this gentleman in the picture, and it's none other than, he needs no introduction, Dr. Hennessy. So it all started in 1981 along with his fellow scientists. It all started in this own campus, Stanford campus. So what happened from then to now? The project that started in 1981, and this is 2019, it has gone through many releases, as you can see, from MIPS 32/64 release 1 through release 6. So that's the latest architecture that we have. And over the course of time, what we have done is we have added many instructions, extensions, and features to enhance the architecture that not only can satisfy the requirements for the low embedded devices, but also the high-end AI systems and different market segments that needs the embedded processors. Now with that introduction, this is a kind of timeline. So this was, we announced, when I say we, now MIPS is part of wave computing. So we announced the initiative or the intent in December of 2018. And then we collaborated with something called open source foundation, called Purple Foundation. And that's where we formed a member committee called MIPS Open Advisory Committee. And then in March 28th, that is less than a month, we actually made all these components available for the community to download and actually work on the stuff real time. With that said, one of the key components, the microAptiv embedded cores, that's still in the, we are testing it. It's in the last phases, and that'll be released pretty soon. So that's going to happen in May. So the key components there are 4 components. As you can see, it's a complete package. You have the architecture, then you have the cores. So the cores are built using that architecture. The FPGA system is more for training, evaluation, and teaching purposes. And then you have the tools. It's a full-fledged IDE, Eclipse IDE, along with MIPS Linux and all the other software that is not only provided by Wave or MIPS, but also from the ecosystem, third-party partners. So as I said, this is available for download from mipsopen.com. You can just go directly to mipsopen.com and download any of those packages. And there are like 4 packages, as I said, and the open course is something that's going to release very soon. So what does the MIPS Open Architecture download package includes? So it includes the latest R6, the release 6, 32, and 64-bit versions. And the SIMD, this is actually popularly used in multiple applications. The DSP extensions for multimedia applications, voice, video, and then you have multi-threading. Multi-threading is a very unique feature for MIPS. That was introduced way back, and we continue to maintain that and enhance that. And Majid is going to talk about the applications where actually multi-threading can be used, for example, the modems, LTE, 5G, and so on. And then we have the MIPS MCU, the micro MIPS for code compression, and the virtualization. Virtualization is another key feature that is available in the MIPS instruction set and architecture for isolation of the secured applications versus the non-secured. The MIPS Open Cores, again, this is something, it's a complete package. It's a production ready package. What this means is it has shipped in millions of devices in the low embedded devices, microcontroller devices. And the package will include the actual Verilog source RTL code. So anybody can take this core and can do their own system on chip right away. It also includes the configuration tools, and UDI is the user-defined instruction, which is if you want to add your own instructions, you have the flexibility to do so through UDI. And we provide enough documentation and examples for you to take that and then do a full-fledged system on chip that will not only have the MIPS instructions, but also you can enhance with your own instructions. Then there is a complete verification test suite and test bench included in that. As I said, there is a whole lot of documentation for you to, with examples so that it will help expedite the process. And the most importantly, we have something called the certification process. Certification process, this really helps to ensure the compatibility with the MIPS instruction set and the course, the way we have developed. So you can take this core and do your own implementation and send the test results to MIPS. So what we will do is we'll ensure the compatibility, we'll verify that and give you a certificate. What this really means is you will now have access to MIPS Open certified trademark. Tools, as I said, it includes, the tools download package includes a full-fledged IDE with QEMU, and we are adding more features, more hardware boards, and probes, and all of that. And then it also supports MIPS Linux and the compilers. So all of these tools are not only available from Wave and MIPS, but also there are a lot of third-party tools that are available for MIPS. The FPGA package is really for evaluation purposes and for teaching. It's a very good tool where we have, this is again based on the microAptiv microprocessor core, but this is a non-production core. It's a fixed configuration core that's part of the package. And there are multiple labs that are available that you can go through, and also an example system on chip design. So a little bit to give you an idea of what the license is all about. So this is an open use license. What this really means is you don't have to pay any license fee. It's royalty free, and it's a worldwide license. You can develop the MIPS Open architecture compliant core. So using the instruction set, whether it is 32-bit, 64-bit, multi-threading, DSP, or all of those features, you can develop your own, core, compliant core. And then you can even sub-license it to the semi vendors, and who can actually then productize it. So, but there are only few, you may not, develop the course or release the cores that are not MIPS Open certified. The reason for that is very simple. We want to avoid any fragmentation out there. We want to make sure that it is compliant with the MIPS instruction. So once you have the MIPS Open certified, you can sub-license it to the vendors. And you cannot mix and match the licenses, which means that the MIPS Open use, you have to strictly abide by the license. And the reason for that is we have licenses for some that are meant for non-MIPS Open cores that are still available. So we don't want to contaminate the two licenses. So it's a strictly follow the MIPS Open license. So this is kind of it summarizes. So if you see on the left, we have MIPS Open FPGA, the package that is available for training, teaching, and evaluation purposes. It's a full-fledged package. It includes, as I said, a commercial a core that is non-production core that you can use and use it for evaluation purposes. Then you can take the architecture and develop your own core, and there are tools available from us, from partners. Then we have a certification process in place, so you can utilize that and make sure that it is compliant with the MIPS architecture. Then once you have done that, you can also add your own customer IP, third-party IP, and then do a SoC design, and then you can literally, anybody can sell or license the architecture, the core to the semiconductors. So at a high level, the features, MIPS is an open use license, and it includes all the components. So the latest R6 architecture, the microAptiv cores, the tools, and the FPGA system. We provide the certification services, and that includes the verification and certification and compliance of the MIPS architecture. And then we also make available the right and license under R6 architecture, the patents, and the MIPS certified trademark logo. And as I said, it is a complete comprehensive package. The benefits, it's a unified approach so that there's no fragmentation. Same tools can be used across the architecture cores that will be developed by the core developers. And so it's same tools, software, and you also have flexibility to add your own instructions through UDI. It's a proven architecture. It's shipped in billions of devices and multiple products from wired, wireless, modems, automotive, and multiple market segments. There is an established ecosystem that is available today, so you can get started right away. It's a mature technology, started in 1981, so it's like 30 plus years of legacy. With that, I'll pass it on to my colleague, Majid. Okay.
Thank you, Saraj. Thank you for inviting us. I'm covering the second part of the presentation, which is focused more on the extensions that are part of the MIPS that we offer most recently as part of the R6 and some use cases. But before I start, I wanted to mention a few words about why MIPS Open, I think, in addition to what Saraj mentioned. Number one is that, well, people ask that there are other open ISAs out there. And, I know you guys coming in a little bit late. And I look at this, we started about 6 months ago, make the announcement, and then now introduced the capability. And when you look at it for the past 6 months, it's effectively almost about 20 years worth of innovation that's been compacted into 6 months. And if you go to our website, or actually MIPS Open website, you're going to see for yourself that the amount of technology and innovation that is available for you to design your next generation server, high performance computing, IoT, gateway routers, or AI platform is there ahead of almost any other open source or capability that's out there. So you can start immediately today implementing your own solution at no cost. It will have cost from anybody else, millions of dollars in upfront and millions of dollars as royalty and stream that you would pay. So all of that is gone and now become available for anyone to use. And the depth and the breadth of the technology and collateral and information that's available as part of MIPS Open is much, much ahead of anything else that's out there. So I am actually at Wave. I started at Imagination some time back and then MIPS. But my actual engagement with MIPS goes back roughly more than 25 years ago when I started at LSI Logic with providing the core to likes of PlayStation, Sony PlayStation 1 and 2, and then working with likes of major telecom and datacom companies of the time, .com, that were designed their products around using MIPS as a means of getting to market faster. Cavium is public, of course. One of the major reasons that Cavium became successful with their technology was utilization of what's available as what's called UDI, user-defined instructions, which means that you can actually say that I can take a few instructions and then compact them into one instruction that does maybe a layer 3 networking processing or a search processing. As a result, I can come with custom instruction and map that to my assembler, compiler, and now I get a boost. And that boost, people claim anywhere from 3 to 10x boost over standard processors. So the UDI has been used with a lot of our architectural licensing customers to implement unique features in software that can boost performance. And we'll talk about some of that. So I'm going to talk about what Saraj mentioned. As part of MIPS Open, we're actually enabling anyone to develop their own core on their own, meaning that you can come to MIPS Open, download today, and start design your core. Sometimes it takes months, sometimes it takes years, and the amount of effort it requires that if you're going after an IoT, less complex to a high-performance computing, it takes a lot more effort. But in order to really help the industry, we also, in addition to opening up the ISA, we're also enabling a few of our cores to be available at no cost. These cores would cost a lot of money if you would have come to us a year ago. Now there is no licensing fee or royalty, and those cores are referred to as microAptiv cores. That's the first line. A microAptiv core is heavily used in many of the IoT applications, embedded, functional safety, and other areas. And then we're making those available. So you can actually start the design today and actually build your product based on a processor and go to market without having to worry about paying any dollars behind it. And also the core is validated. I don't know if Saraj mentioned, today we are shipping more than 1 billion devices that are based on MIPS core. We are in tens of billions of dollars, tens of billions of units of cores. So it's proven, and we have track record. So there's no concerns about using the core, and all the features are available for you to use. As Saraj mentioned, some of the unique values that customers of MIPS continue to use our solution when you look at our websites and search for MIPS is multi-threading. We have a good presence in the automotive space. We have a good presence on 5G and networking, data center acceleration. And multi-threading is one of the key features that differentiates MIPS for a lot of these embedded applications. And we'll talk about the how, why. We also have hardware-backed virtualization. If you're trying to run, let's say, multi-tenant environment, it used to be only for a data center. Now we're seeing multi-tenant applications find their ways into the embedded space. So virtualization is one way to do it, but we add hardware support for that. So as a result, it improves the performance of the platform. We'll talk about that. SIMD, which is single instruction, multiple data, is also another capability for doing, let's say, if you're doing some AI functions, DSP functions, floating point functions, and if you're looking for dot products, SIMD is actually a very efficient engine that is bolt-on to the core, so allows you to enhance your compute power and improve your compute power enormously, actually. And I will talk about some use cases. So this first slide is actually talking about the open use core that I talked about, microAptiv. MicroAptiv is a core that is developed, is a 32-bit based on MIPS 32. It's a 5-stage pipeline architecture. Unlike its competitors, it actually has a lot more registers that you can have freedom of managing your application more effectively. Interrupt latencies are quite fast for a lot of these applications because we have what we call shadow registers, for example, that you can shadow applications. So if an interrupt comes, you can actually almost instantly jump to interrupt without having to do a lot of push and pop from the stack. Those are very helpful. It provides a DSP ASE application-specific extension, and I think it brings the best of its class as far as the core mark or DMIPS. And for this class, you can easily get to 3.5 core mark or 1.7 DMIPS per megahertz. The device, besides the shadow register that I mentioned, it's a RISC engine. So it's a single cycle per instruction, simple memory addressing mode, but it also has what I refer to as the UDI. If you can look at this part. So UDI is, as I mentioned, user-defined instruction. So we're going to do a lot more work with MIPS Open community to, for example, define maybe AI extensions or other extensions that you would find and create a capability around the UDI to enhance your application. So UDI is means to expand the instruction but maintain uniformity on the operating systems and compilers and assemblers. This core is going to be available for download within a matter of days or weeks, and you can check the MIPS Open website for that information. Now, there are two different flavors of the core. One is the UP, one is MP, that allows you to be able to run, if you're running Linux, you can run Linux. If you don't need to run Linux, you don't want the complexity, you can actually use a simpler form of the MMU to manage your RTOS or bare metal applications. Very popular core. As far as performance, it clearly beats the competition of the similar core. It's in its class when you compare to PPA, performance power area, at 40%, and performance, and in case of DSP applications, you get 90% boost. So next, or first item I was going to actually cover is, the virtualization, as I mentioned, and multi-threading. So, if you guys are familiar with virtualization, is the intent of virtualizing a CPU is, in this diagram, is ability to create contexts that you can separate. And this can be done purely in software, meaning that you get an interrupt, the red columns at the bottom are a privileged state, and you get those interrupts. You can actually switch your application from one to the next. That time, T time, can be changed based on the tick of your desired application. So you can, in this case, for example, we have 4 tenants or 4 clients or 4 guests that are running. Since the intervals are pretty small from application perspective, you don't notice that you're actually switching, but effectively you're switching from one application to the next application. And there is what's called a hypervisor that you see. The function of the hypervisor is to switch these contexts. So when you're only looking at software mechanism in doing that, what happens is that there is a lot of overhead. Because if you're running in one client running, let's say Linux, the other client is running Windows, then you have to do a lot of flushing and cleaning up of the CPU and its environment from Linux and setting up the Windows and then bring up the Windows and run. So the overhead is quite significant, and some of that has to do with flushing the cache, registers, and so forth. So what we have done is that we have added hardware support for some of those. So the overhead associated with these switchovers are minimized, and allows you to do context switching easily at almost 10x of what a software version would do. So this is available. So if you're trying to say, I'm going to develop a next generation server that needs to have support for multi-tenants, you can actually take advantage of the virtualization to be able to do that. Or for that matter, I have an access point, a router, a gateway that I will have a client application versus my home application. Maybe it's, maybe a Verizon application, wants to allow someone else to program. So now you can actually create separation. So OS 1 can be the home product, and then OS 2 can be guest product. And that's actually becoming quite critical in almost every embedded application, whether it's an automotive or gateway or router. So ability to context switch, but then at the same time, you want to make sure it's secure and safe. And then we'll talk about how you can actually assure that these isolated environments are protected, because you don't want contamination. You don't want cross-contamination of one operating system to the other one, or eavesdropping or monitoring. So the hardware actually creates clear separation. That separation protects one operating system from the other one. So that's part of what the hardware's virtualization offers. Separately, you have simultaneous multi-threading. In the case of simultaneous multi-threading, it kind of looks the same, but in this situation, we have different cores. You can have, let's say, 4 threads, you can 2 threads or more, but in the context of multi-threading, you're actually doing context switching at a clock rate. So effectively, you could have 4 operating systems concurrently run. Putting in simple terms, if time is 100%, in this case, each operating system gets 25%. Not necessarily, we'll talk about that, but there's benefit into multi-threading as well. We'll talk about what is the benefit. Now, someone can actually take the virtualization technology and multi-threading and combine the two. Now you can actually benefit from concurrency while you're actually ensuring isolation in some situations. So there is a lot you could do at this point, and many of our customers take advantage of these type of situations, which we'll talk again later. So in the case of multi-threading that I mentioned, where you have concurrency, basically what it allows you to do, because you're taking a CPU resources and multi-threading it at the hardware level, not the software. This is very different than software threads. It's actually hardware threads. And the hardware threads allow you to actually get a boost. And we have seen ourselves in our lab and doing a lot of benchmarks, as much as 60% instruction per clock boost. What does that really mean? Or why is that actually? It doesn't solve every problem in the world when it comes to software. What it solves is that if you're trying to reach out to an I/O, generally in the case of a hardware, when you're reaching out to I/O, whether it's Ethernet or USB or PCI Express, and trying to read, it's in the order of 10 cycles to hundreds of cycles, depending on how far the I/O is from the CPU and what the latencies that are there for a round-trip delay if I want to read something from the I/O. So for the time that you're waiting for I/O, you more or less become idle because you have to wait for results. With multi-threading, what happens is that you actually replicate the instruction flow in such a way that you can actually have second independent flow that can take advantage of the resources of the CPU, so you don't make sure that utilization of those resources are improved. So as a result, if you have two threads running, one thread can be waiting, and if it's waiting, you actually let the hardware allows the other thread to start utilizing the resources. And as a result, you get a higher boost in running your CPU. So we have seen as many as 60%. We have customers that did their own architectural license and said, hey, you know what? I have a networking application. I want to do heavy distributed workload processing. I want to create my own 12 threads. I put 12 threads, use the same resources because for example, an Ethernet environment, I got to go after 12 ports, and each one will take time, so I can have a better utilization while I'm waiting. I can use my utilization better. In that context, I can get even to 100% improvement in utilization when you compare it to a single-threaded environment. So you get higher throughput, put much less energy into it. If you actually go to the website and search for, let's say, MIPS and MediaTek, one of the folks that are doing 5G technology or 4G, they clearly endorse the fact that multi-threading in this context allowed them to keep the same envelope of power while improving the throughput. Because now you get a lot more while you're maintaining the same. So multi-threading is very effective for many applications out there that can be taken advantage of a distributed workload processing. In addition, when you have multiple threads, you can say, you know what, I'm going to take thread 0 and assign it to interrupts. Not, if you remember from the diagram before where you had 4 of them running, if thread 0 was assigned to interrupts, you can actually park it and make it wait for interrupts. So the moment interrupt happens, what happens in a single-threaded environment? You have to push everything on a stack. There's a lot going on before you can even service the ISR. To service the ISR could be hundreds of clocks, sometimes thousands of clocks that takes to go from one context, that's in this case an ISR or an NMI that comes in. So you can avoid that. You can actually say my highest critical application or events that I need to respond to, it would assign it to thread 0. When the interrupt happens, I jump. And that jump is literally instant. So now you can say that, okay, now what, if I'm an automotive, every clock cycle counts for autonomous vehicle. I cannot afford waiting when I see an interrupt comes and says, I got to turn left. So those are some of the critical elements that attracts our customers saying, yes, I'm going to use multi-threading, and I'm going to use it in such a way that I can use these threads for getting response times faster to my application. So clearly what we call zero or low overhead for interrupt response, whether it is a 5G application, whether it's autonomous vehicle, whether it is other applications that require instant response to an event. And we're kind of starting to see a lot of those. But there's a drone going on and have to look at something that's obstruction or some other, the response time have to be much less, and sometimes today is measured in microseconds. And I'm expecting that actually starts to drop to nanoseconds of response time as we need to get these applications running and responding quickly. The other thing is, of course, you can actually use multi-threading. As I said, there are 4 threads, let's say, in this example that I've shown. So you can actually, from a Linux perspective, you see 4 CPUs. So literally, it's like a 4-core. So Linux, you can actually specify how many cores you see from Linux. And in case of multi-threading and this particular use case, you can say, I'm going to run an SMP Linux. How many cores do you have? 4. All of a sudden, you actually see a 4-core, where it's actually a single core, but it has 4 hardware threads. Or you can say, I have 4 distinct different applications, as I mentioned, and I can run AMP application, asymmetric multiprocessing. And I see 4 CPUs for 4 distinct separated stream of instructions. So it could be completely different. One could be RTOS, could be Linux, one would be control, and one could be interrupts, for that matter. So multi-threading provides a lot of different ways to benefit from improving throughput, utilization of your instruction, And as a result, you can either get headroom or lower your power. And you actually get more faster response time. All right. So this is trying to explain, for example, the example that I've shown. Thread 1 to thread 4 are actually 4 distinct instruction flows. It's like, thread 1 could be a Linux, thread 2 could be an RTOS, thread 3 could be a bare metal, and 4 could be an ISR. Completely coming from different part of the memory. They can be booted separately, independently. But what happens is that all 4 of them are running through the same, and as you can see, they can actually utilize the resources and the execution queue and the pipeline. And actually, the execution unit can be now shared. So if thread 1 is waiting for a response, thread 3, 2, and other threads can utilize those resources. And that's how you get what's called instruction per clock, higher. When you look at a single threaded application, whether it's anybody, Intel, ARM, MIPS, PowerPC, Spark, when you look at those processors, in a typical application, an IPC or instruction per clock, and I'm just throwing a number, but generally is under 1, meaning that because I have to wait for a response from, I have a cache miss, so I got to, reload. It takes time, so I have to wait. Those waits translate to stalls and translate to taking your instruction per clock lower than 1, sometimes averaging 0.7, 0.8. In this situation, as I mentioned, you get 60% boost, so you can actually get to 1.6, 1.7. Depends how many threads you're running. So depending on the workload, you can actually get a lot of efficiency out of multi-threading. And people that understand it can take advantage of it. And you've seen this heavily used in the storage application, networking application. Most recently, if you look at web and Google us, you'll find this in automotive space. You find us in modem space. That allows you to get higher throughput, maintaining your power envelope. Same. So again, as I maybe talked, anytime that you need to do parallel processing. What is parallel processing? Distributed workload is one example. When you have multiple OSs running, or a single OS in a SMP environment. When you have multiple workers, when you have function sensitive to context switching between tasks, when you want deterministic behavior, that's another one, right? Automotive, when I need to turn left, that's autonomous car. I don't want to wait. I want to make sure that I jump into that event, respond to it instantly. So there are many ways of doing it. This way you get a lot more efficiency. Because if the decision to turn left in a car is based on thread 0, it will instantly respond. If that thread is a software thread sitting in a major instruction flow, you actually have to do a lot of cleanup before you can service the ISR or NMI. So that translates to, if you have another NMI that's happening, how do I respond to it? So you get to a situation where you have a variable length response time, so deterministic behavior is not guaranteed. So as I mentioned, ADAS networking, VoIP, and other areas, this is quite useful. So I'm going from multi-threading to virtualization. Now, it's very different concepts. On the left side is a non-virtualized environment. You have a Linux kernel, you've got a user space, and the kernel is privileged. All your drivers are at the kernel level, managing resources. Memory is managed through the kernel. So in the case of left, you have a TLB, a traditional TLB MMU that can under control of the kernel level, that protects the memory, allocates memory, releases memory, and so forth. The user is limited. But in this situation, if you want to have multiple environments running, then you actually have to manage the new user. If the user is on Linux and you want to have two Linux running, it becomes quite challenging on the left side, because now you have to manage the TLBs and MMUs and caches and lots and lots of resources to protect them or isolate them. With hardware virtualization capability, which is some of the capability that we are actually providing through MIPS Open, now you're able to actually have, from the right side of the diagram, 4 levels. You got the root level. If you remember from that diagram that the root was at the bottom. The root level here is the privileged state, most highest privilege state of the CPU. And then you can have, excuse me, guests on top. The guests are the tenants or the virtual machines. These guests are intended to be no different than this configuration on the left. So literally, if on the left side you were running a Linux, that exact environment can be just dropped into the right environment and it will just run. You don't have to really make any changes. So from Linux perspective, it doesn't know it's virtualized. But there is hardware element that actually creates that separation. So you can take the same exact Linux and copy it twice, drop it there, and they wouldn't even know that there are 2 copies of Linux running. That's obviously normally the trend with virtualization and the hypervisors. But in this case, there are hardware mechanisms that enforces those isolations and doesn't require the software to do a lot of cleanup once you're doing a context switch from one Linux to the next. When you power up, generally, actually all the time in this fashion, you would normally boot up to the root context. Now you're actually coming to the root context, which is the most privileged state. If there was any type of root of trust or any type of secure boot, you want to make sure that the root context is authenticated, validated. But once you get to the root kernel and you're starting to establish and initializing the entire system, then you can decide, okay, I want to bring first guest up. I want to bring a second guest up. And the architecture that is available through MIPS Open allows to handle up to 255 guests. In the embedded space, we haven't really seen that many guests. But let's say if you want to develop a NIC that needs to handle a server, a space that requires 128 clients, you can actually enforce in a CPU 124 environments that can be completely isolated and protected from each other. So what's called a guest ID, as you see on the diagram, is an 8-bit value. What we have done at MIPS, we use 3 bits, 4 bits, 5 bits so far. That allows us to get up to 7, of course, 15 or 31 environments that can be isolated from each other. And customers use them in that fashion. Have one assigned to security, have one assigned to application operating system or RTOS and so forth. So the guest ID is a mechanism to enforce the isolation. And guest ID is under control of the root. So there is no possible or easy way or possible way that the guest can actually manipulate or alter the state of the root. Because for one, the registers that are in control of the root are not visible to the guest. However, the guest registers are visible to the root. So root is the privileged state, can see everything, but every guest only sees its own resources. So as a result, you can create environments that are fully, I would say, protected or separated or isolated. It's not necessarily secured. Security is a different discussion, but they're clearly enforced. You can enforce policies to separate these environments. Whether you want to call them guests, tenants, or virtual machines. This is another way of looking at it, maybe easier to see, but the root context, as I mentioned, is a privileged state. You can actually have isolated guest contexts. There are different means, as that's shown here. When reset happens, you actually start at the root context, root kernel, and then you can initialize the system and enable different guests. But if there are mechanisms to actually request for service from the root context, and those mechanisms are also displayed here, where you can actually either, for example, you have a USB call, or you're doing PCI or Ethernet. You can dedicate the I/O, that in that case an Ethernet port, to guest number 1, and Ethernet port 2 goes to guest number 2. So you can actually also program that interrupts are directly handled through the specific guest and only handled by that guest. But if you want to share resources, you can say, you know what, I just don't trust any of the guests. I'm going to put all my resources in the root context and actually make those requests through the root. So there are mechanisms to actually communicate between the guest and the root, looking for services, looking for memory allocation, memory, and other means. So it is intended to make sure that the root context has full control and can allow a guest to have also a lot of control. But the guest cannot really influence the root. And you can always go to the root context and manage your entire system in that environment. So you could clearly create environments that can also be secured. In this case, again, we're showing that there's multiple OSs running. Root can be a secure hypervisor. It can be, so you could actually design your system that saying that I want to make sure my root context is secure, and as a result, I can count on it. It can be a chain of trust for my root of trust. So in that situation, as you're booting up, you have authentication mechanism. It comes up, authenticates your kernel, root kernel, and then brings it up. At that point, is a chain of trust. They can actually start further authenticating the rest of the system. So root can actually be a secure hypervisor and managing guests. Guest access rights are controlled by root. So it's clearly, you can actually enforce those policies through the root. If for any reason one of the operating system is corrupted or hacked, or the hypervisor or the root can actually initialize, reset, reboot that particular environment without affecting the rest. So if you're seeing misbehavior. So as an example, if in this case, guest 1 says, you know what, it's been hacked and it's trying to access the resources for guest 2. So it's okay, I figured out how to get access to guest 2, so I'm going to start eavesdropping or trying to access the Ethernet port or memory map of the guest 2. The moment that access happens, there is an exception to the root. The guest 1 is trying to attempt to reach to guest 2. Now, if it happens often, sometimes it's maybe a bug in the software, or sometimes intentional. So at that point, you can actually have rules to say, okay, know what, if there's repeating access to guest 2, something's wrong with guest 1. So either report it or even initialize it. So that mechanism is available to control. A very good alternative way to enforce security policies for your environment at the hardware level. So you can, as I mentioned, handle up to 255. We haven't seen that many, but that's the as far as the R6, MIPS R6 instruction set. 255 is the number of guests you can support. So you could decide that certain interrupts can actually be directed to the guest. You know what? I want to give USB control to guest 3. Or Ethernet is shared, so let's move that to root. Or Ethernet 4 is needs to be shared, so create a proxy through guest 7 that can actually decide who to pass it to. So many flavors of managing this. The most important thing is that there is a lot of, at least you can actually implement a lot of hardware support to reduce the overhead associated with context switching. And that's critical for many of these applications. Next thing I was going to mention, and these are, by the way, the capabilities that is available through MIPS Open R6. So if you want to create your solution for next generation products, it's available now. You don't have to create a working group to do it. It won't take you years or months compared to other ISAs that are still in this infancy. That's a big thing to notice. This has been there for 3 decades, and we compact those 3 decades into a few months and make it available to you. With other open source solutions, there's a lot of work still being done, but here you can get off the ground running. Next item is the what we refer to as MSA. So it's actually the SIMD engine that's also part of the R6 extension. This example of what we have done at MIPS Wave Computing, but this is just an example of a CPU that is got. Actually, I'm not sure which core is this, but regardless of that, I'm going to cover those sections and focus just on a SIMD portion. SIMD is actually an engine that sits next to the other execution units like your ALUs and other functions, and its intent is to do DSP functions, floating point functions, or any other type of mathematical functions or ALU functions, but in a context of a dot product or a vector type of product. So you could design your SIMD to your desired size. In this particular example is 128 bits wide SIMD. We have roughly, I think, some 150 instructions just for the SIMD, meaning that you can do dot products, MAC, multiply, accumulate functions. So it's pretty useful for running, let's say, TensorFlow, Caffe, or any of these algorithms. It's not necessarily, it doesn't compete with dedicated hardware for AI, but if you're doing learning, for example, there's floating point engine that's there as well. So you could literally design your next generation AI based on your particular version of SIMD that is tailored and can be efficiently scaled for the application that you're going after. So as a 128-bit vector, you could make this SIMD to handle, for example, 16 8-bits, 8 16-bits, 4 32s, and 2 64-bits, integer, floating point, Boolean, or arithmetic operation. So in this case, we have the instructions that are defined for those, so you can immediately implement yours. Corresponding, we have actually 32 as well SIMD registers. Those are also 128-bit wide. So you can actually have, let's say, your weights for your convolution 3x3 stored in the register, and actually don't have to go back to memory all the time. It does give you a boost in improving some of the algorithms for your application. So SIMD is quite useful for many of the applications. I think I'm going to go through showing you, in this case, how the SIMD operates, and also in the context of multi-threading. So not all of you guys are going to design a product that has SIMD, virtualization, and multi-threading. But we have, because we normally develop general purpose processors, but you could decide to do that. And this is one use case. In this particular case, you have an application flow that has some DSP algorithms. So from time to time, you call this DSP algorithm to run, whether you have a SIMD or DSP engine. That instruction flow is inline. Means that you have to run the green instructions first before you get to the red instruction flow. You can do software multi-threading, but effectively you have only a single stream of execution. With multi-threading and SIMD, now you can actually, let's say, assign your DSP algorithms to be dedicated to a thread and the SIMD engine. And quickly, what happens is that you're separating your normal instruction flow. Let's say Linux calling some DSP algorithm, and all of a sudden, you're first of all, you're separating it, And then second is that you're actually utilizing different hardware resources on the CPU. And as a result, you immediately get enormous amount of boost for your application. You can actually take it even further and add additional threads. Now in this case, now you can actually get, again, more and more throughput because you're taking advantage of multi-threading, and those threads are assigned to a DSP algorithm. Maybe one is a conv 3x3, one is a conv 7x7, convolution 7x7, or other algorithms, so fill filter or others. But we have done a lot of tests, and our customers also use it, where we see having to separate these functions. You can quickly get the IPC up, instruction per clock, for that particular area of the CPU. So quite effective method of boosting your application throughput. This is a use case that's actually in production today. It's benefiting from a number of things, but one of the main things is multi-threading. In this case, you have a RF front end. You got the baseband type processing, and then you have the control. Once you do the baseband, figure out the data, then you actually have to pump the data to the application processor. But one of the challenges is that in a 5G environment, it's enormous amount of data that has to come in. And in order to really handle this, you end up having a lot of processors in parallel. And we have demonstrated that actually you can reduce those number of processors to a lot less by utilizing multi-threading. Now, in this case, some of the cores we have, for example, allow you to have up to, let's say, nine threads. So you could effectively say, thread 0 handles this interrupt, and you can actually start assigning threads. And what does that mean is that when the data is available for a specific flow, you can instantly respond to it. You don't have to push and pop from a stack. You don't have to flush the cache or other means. You can actually jump to it and quickly respond to that particular context. So it translates to executing less number of instructions. And typically, when you do that, you end up burning less power. So effectively, you can do more. Either you can do more, or you can reduce the power. So this is a true example of it. Either through the data path or the control or the interrupts. So you can probably look on the web, and there's a lot more information. But my intent for this slide is that to perhaps encourage that there is a lot you could do with this type of context switching with our multi-threading capability. Now, for example, in this case, you have 4 CPUs and 9 threads. That's one of the use cases that we have. 4 times 9 is literally 36. So you could have this system that you can have 36 different contexts in a small environment ready to go. You can assign 36 interrupts or 36 events if necessary. You can group them together. So there is a lot you could do, and again, that becomes what's called a microarchitectural step that you have to take. And design A may be slightly different than design B and design C, and that's the approach MIPS has been taking for, of course, generations and decades. But now we're making that available for you guys to go and try that on your own. And actually it's ready, proven, and working. I think that's my last slide, right? So I'm going to hand it back to Saraj, but I'm here to answer questions after the presentation. Thank you for your time. Very nice. Thank you. I take that back to the architects. Thank you.
Thank you.